Chapter 15. Uh, and especially about strong acids and bases. And then in chapter 16, we will focus more on weaker bases. We touched a little bit on acids and bases back in chapter 4, just enough to get us to be able to use them, but now we're really going to focus a bit more on them. Right, so back in chapter 4, we talked a little bit about acids and bases and some common acids and bases that you're familiar with. Of course, a lot of acids are things like fruit juice, lemon juice, orange juice, vinegar. Aspirin is actually a weak acid. And in general, acids are sour. Bases, which tend to be things like ammonia, lye, soap, these are all basic. They tend to be bitter. Also, baking soda is a base. I don't like to taste that very much. All right, some other things about acids and bases is that they will change colors of indicators. So in lab, we use litmus as a test to see if something's acidic or basic. Acids will turn litmus red, bases will turn litmus blue. There's some other indicators that if you haven't used them already in lab, we will be using them. Phenolphthalein will be colorless in acid and pink in a base. There's bromothymol blue will turn from yellow to blue. And then the other thing about acids and bases is that they neutralize each other. All right, so the first part of this chapter, we're going to look at theory of acids and bases. So the first one we're going to look at is called the Arrhenius theory, which is the most basic. The Bronsted-Lowry concept takes the Arrhenius theory just a little step further. It's a little more useful and expansive. And this is the Bronsted-Lowry is the one we're going to focus on the most in this class. And then we'll briefly talk about what the Lewis acid-base theory or concept is. So like I said, this will expand what you learned about in chapter 4. All right, so the Arrhenius concept of acid and base. An Arrhenius acid, Arrhenius was someone who studied this back in the 1880s. So an acid is just a substance and when dissolved in water increases the concentration of the hydronium ion. H3O plus. Remember that H3O plus hydronium ion is often used in the same way as H plus. They can be used interchangeably. So the H plus hydrogen ion and the H3O plus is really the same thing, and that can be used interchangeably. And sometimes you'll also hear the word proton used for H plus. Okay, the H plus really is a proton, but it's not a proton in the sense that it's in the center of the atom. It's a hydrogen ion being changed over. So again, remember that H plus does not actually exist by itself, and so it's always chemically bonded to water. So H3O is the more appropriate way to write an H plus ion, H3O plus. In fact, H3O plus is actually then also attracted to other water molecules. So usually you'll see a big sort of a bunch of molecules all together associated with a hydrogen ion. All right, now a base in the Arrhenius concept is a substance that when dissolved in water increases the concentration of hydroxide ion. Now, a strong acid is a substance that ionizes completely. So, for example, perchloric acid, HClO4, when it dissolves in water, will completely dissociate to give H3O plus and ClO4 minus ions. Other strong acids are HCl, HBr, HI, HNO3, and H2SO4. So you should make a note to remember these 6 strong acids. It's really important. It'll especially be helpful to you when you go on to chapter 16 if you can remember these 6 strong acids. These are the 6 acids that we're going to deal with that completely dissociate in water, and it'll make a difference to the type of problems that we do. Okay, so Now, a strong base is a substance that ionizes completely to give OH negative ion and a cation. So an example is sodium hydroxide. When you dissolve it in water, it completely hydrolyzes to Na plus and OH negative 100%. And then the other strong bases that, again, you should remember: sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. You'll notice where they are on the periodic table. That might help you remember. So lithium, sodium, potassium are all in line. And then if you cross over to calcium in the second row, calcium, strontium, and barium are all above each other. And then the strong acids, you notice the Cl, Br, and I are all in the same column. And then you're just going to have to remember the other ones: nitric acid, sulfuric acid, and perchloric acid. Okay, so all other acids and bases, now there'll be some other strong ones that we're not going to deal with, but most all the others are considered weak. And why is that? Because they are not completely ionized. So they exist in a reversible reaction or in an equilibrium. So an example of this is acetic acid, HC2H3O2. When it dissolves in water, only a small percentage of it will dissociate to become H3O plus and the acetate ion. This is a good time to refresh your memory. Remember that not all acids are, not all H's are acidic, so they're not all considered acidic. And in general, when we study acids in this class, to make it easier, the H's that are on the front of the molecule are the ones that are considered acidic. And so sometimes you'll see more than one in the front, and then we know they're all acidic. But if you see some stuck in the middle, like the H3 here, those are not considered acidic, so only one of them. You take the H from the front. Anyway, acetic acid only partially dissociates, so a small percentage will dissociate and a larger percentage will stay as the complete molecule. Ammonium hydroxide is a weak base. Again, only a small percentage of the NH4OH will dissociate to give you NH4 plus and OH negative, and a larger percentage will stay as the complete molecule. So again, acid-base strength has nothing to do with concentration, but rather how much it will dissociate the H plus or the OH negative. So the Arrhenius concept is limited because it looks at acids and bases only in aqueous solutions. And then it also singles out the OH negative as the source of the base. And there are other bases besides just OH negative. For example, NH3, ammonia, is a base. And it's hard to see how it's a base just by looking at it because the OH negative is not apparent. And so a broader definition is going to be discussed next. Actually, two broader definitions, but we'll focus on one and I'll introduce the other. So Bronsted-Lowry is just an expanded version of the Arrhenius, and just a little bit more detailed as to what an acid and a base is. And so just keep in mind that if something was an Arrhenius acid, it's still an acid under the Bronsted-Lowry. So things don't switch up that much. It's just a different way of describing how something's an acid or a base. And an Arrhenius base is still a base, but now we're again expanding it so other things might be considered acids or base. So according to the Bronsted-Lowry concept, an acid is a species that donates a proton or donates an H plus in a proton transfer reaction. And then a base is the species that accepts the H plus in a proton transfer reaction. So an acid-base reaction is basically a proton transfer reaction. So and also keep in mind that because most of these acid bases are reversible, we're going to have a proton transfer in each direction. So it's really just who wants the H plus more. And so it's going to transfer one way, and then if we look in the reverse, it'll transfer the other way, which you'll see in just a second. So if we look at this reaction, NH3 plus H2O to give us NH4 plus and OH negative. So we can see how NH3 is a Bronsted Arrhenius base because it does promote OH negative, but we're going to look at it a little more detailed. So what happens is that you can see by inspection that the NH3 on the right-hand side becomes NH4 plus. So what's happened? It's gained an H plus. So whichever species gains an H plus is the base, or accepts a proton. So the NH3 is a base because it accepts an H plus, accepts a proton. In the same way, the H2O, if you look by inspection, H2O becomes OH negative. So in the process of this reaction, the H2O has given away the H plus. It's an acid in this situation. So NH3 is the base, H2O is the acid, and there was an H plus transfer from the H2O to the NH3, from the acid to the base. If we look at the reverse reaction, you can see the blue arrow highlighted going backwards. We can also do the same thing. So if we look at NH4 plus and we look at NH3, in the process of going from NH4 plus to NH3, NH4 plus has donated an H plus, so it's an acid. And in the process of going from OH negative to H2O, OH negative has gained an H plus, so it's a base. So NH4 plus is an acid, OH negative is a base, and in the backwards reaction there's a proton transfer, again from acid to base. So in any acid-base Bronsted-Lowry reaction, we always have two acids and two bases on either side, or well, one acid and base on each side of the reaction. Two total acids, two total bases. Now you can see that if something is just connected by an H plus, so the only difference they have is an H plus, these two species are called conjugate pairs of each other. So they're conjugate acid-base pairs. So NH3 is the base, NH4 plus is its conjugate acid. You could also say NH4 plus is the acid, NH3 is the conjugate base. The main thing is that they're conjugates of each other. So again, a conjugate acid-base pair are two species in an acid-base reaction. One is an acid, one is a base, and they only differ by the loss or gain of a proton. So they only differ by an H plus. So the acid always has the extra H plus and the base doesn't have it. So NH4 is the conjugate acid of NH4 plus is the conjugate acid of NH3, and NH3 is the conjugate base of NH4 plus. In the same way, H2O and OH negative are conjugates of each other. H2O having the extra acid, having the extra H is the acid, OH negative is the base. Just keep in mind that a Bronsted-Lowry concept says that something is an acid or base by its function. So by its definition, if something gives up an H plus, it's an acid. If something accepts an H plus, it's a base. And what we'll notice is that some things can do both. And so it's a matter of function, and you have to look and see what it's doing in that particular reaction to be able to identify it as an acid or a base. So let's just take a minute and determine which are the conjugate acid-base pairs in the following reactions. All right, so HCl and H2O. Oh, and just keep in mind you should always have one acid and one base on each side of the arrow. So if you find yourself putting two acids on the same side, you've done something wrong. All right, so let's just inspect HCl. On the left, it's HCl. On the right, it's Cl negative. So HCl is the acid, and then Cl negative is this conjugate base. So it must be true that H2O is a base, but let's inspect that some more. So yes, H2O becomes H3O plus. So H2O is the base and H3O plus is the conjugate acid. The one that has the extra H plus is the acid. All right, so in a similar way, HNO2 is the acid and NO2 negative is the conjugate base. H2O then is the base and H3O plus is the conjugate acid. Okay, finally, now this one could be a little bit harder because you see that both species on the left have an H in the front, so they could both potentially be acids. But again, you have to tell what's happening in this particular reaction. So HCO3 negative, when you go to the right, you see it becomes H2CO3, so it has gained an H plus. So HCO3 negative is a base, and then H2CO3 is its conjugate acid. And then HF is the acid, and it does give up the H plus to form F negative. So that's the conjugate base. So if you have an acid or a base already, you can find the conjugate just by, if you have a base, and you want to find the acid, you add an H plus. So don't forget the charge is really important. So you have to increase the number of H's by 1, but you also have to increase the charge by 1. So if you want to know what is the conjugate acid of H2PO4, well, we have to increase the number of H's by 1, so it's H3PO4. We increase the charge by 1. Since it's a -1, it becomes neutral, 0 charge. Don't forget that 0 charge. A lot of students forget it. It goes from -1 to 0 and then 0 to +1. So OH negative will become H2O. It's one of the weird ones where you swap it and you write it. Normally, for the most part, just write it in the front. H2O is one that gets swapped around. So Cl negative will become HCl. HCO3 negative, again, we're going to add an H, so it becomes H2CO3, and because it's a -1, it'll become neutral. CO3 -2, however, again, to find the acid, we just add one H, so it's HCO3, and we go from a -2 up to a -1. H2O, if we add an H plus, becomes H3O plus, and then NH3 becomes NH4 plus. And again, NH3 is one of the weird ones that you don't write it in the front, you add it to the H's, and if you wanted to write HNH3 plus, that would be fine. So to find the conjugate base, you remove an H and you decrease the charge by 1. So H2O, the conjugate base of H2O will be OH negative. The conjugate of HF will be F negative. The conjugate base of H2S will become HS negative. If it's already a -1, it'll become a -2, so H2PO4 will become HPO4 -2. HPO4 -2, you can still remove another one. That'll become PO4 -3. And then HCO3 negative can remove one and become CO3 -2. Notice some of these can go both ways, and we'll talk about that in just a second. All right, so some species can act like an acid or a base. This is called an amphoteric species. It can gain or lose a proton. So for example, we just saw this, HCO3 negative can donate an H plus and become CO3 -2. So HCO3 negative can act like an acid if you've got a strong base around. But it can also act like a proton acceptor and become H2CO3. So it can act like a base to become H2CO3. So the amphoteric characteristic of water is very important to acid-base chemistry. And so it's clearly the most amphoteric substance around. So again, water can react with a base by acting like an acid. So H2O can donate an H plus to become OH negative. Water can also act like a base and accept an H plus from an acid to become H3O plus. So this is a very important property of water. So just to summarize the Bronsted-Lowry concept, a base is a species that accepts protons, and so OH negative is really only one example of that base, of a base. So there could be other things that are bases. An acid then, of course, is something that donates a proton. It can be anything can be an acid that has a proton to donate. Acids and bases can be ions or molecules. Acid-base reactions are not restricted to just aqueous solution, unlike the Arrhenius theory that said it had to be dissolved in water. You don't have to have water at all. And then finally, we know that some species can act like an acid or a base, depending on what the other reactant is. So these are all really important things to keep in mind. We're going to come back and use the Bronsted-Lowry theory some more, but I'm going to introduce one more theory just really briefly. Okay, so the Lewis concept of acids and base defines an acid as an electron pair acceptor and a base as an electron pair donor. And I know you see that the words are kind of flip-flopped from what we saw before, but notice what it is. It's doing something different. It's not talking about protons anymore, but it's talking about electron pairs. And so again, this is just another definition. It doesn't change anything that we've talked about. If something's a Bronsted acid, it's also a Lewis acid. If something's a Bronsted base, it's also a Lewis base. but this expands our definition just a little bit more to include other things. So it can include reactions that do not involve H pluses. So let's look at a few examples. All right, so this was one that you wouldn't think of as an acid-base reaction, but in fact, in the Lewis definition, it is. So NH3 can act like an electron pair donor. So an electron pair donor or a base. BF3 can act like an electron pair acceptor, and so it can act like an acid. And then we end up with something that's an acid-base complex. So that's kind of interesting. But again, what I wanted to say is that the definitions are just a different way of looking at it. So if you look at this reaction of NH3, ammonia, plus water, it's still NH3 is still a base no matter how you look at it. It could be a base by the Bronsted definition that it's an H plus acceptor. So you can see that NH3 has accepted an H plus to become NH4 plus, or it could be a base by the Lewis definition where it actually donates this pair of electrons to grab that hydrogen. So it actually shares those electrons with the hydrogen, so it's an electron pair donor. And then H2O is an acid no matter which definition you use. Either you can say, well, it's an H plus donor because it gives up the H plus, or you can say that it's an electron pair acceptor because it was originally sharing an electron pair with the hydrogen, but hydrogen gets removed, and so those electrons end up only on the O, and so it gets its electron pair that it used to share. So it's an electron pair acceptor. So it's just a different way of looking at it. And if you go on and take any more chemistry, the Lewis theory is used a lot, especially in organic chemistry. All right, so let's talk a little bit about relative strengths of acids and bases. Because there's this conjugate acid-base pair, and because it's always a proton transfer, really what an acid-base reaction is just a competition between the two different species for the H plus. So if something is really good acid, it's really good at giving up the H plus, but then its conjugate's not going to be very good at accepting it back because it either really wants to get rid of it or really wants it. So it's a competition. So who wants that hydrogen more? And so whoever wants it more will end up with it. And so we can actually order acids by their relative strength as to how much they're willing to give away their H pluses. So again, stronger acids are those that are more willing to give up H pluses. And then a weaker acid is less willing to give it up. And similarly, a strong base is one that's really willing to hold on to a hydrogen or really willing to accept it. It's going to be much less willing to give up. So there's this sort of a inverse relationship between acids and bases that we'll see on the next slide, or on the next slide after this. So here's again, here's an acid and a base. Acetic acid plus water gives us H3O plus the acetate ion. And again, it's a competition for who wants the H plus more. So what you can look at is you say, okay, there's HC2H3O2, the acetic acid, and then the other acid is H3O plus. Who wants the H plus more? Well, actually, the HC2H3O2 does, and so the equilibrium is skewed to the left. That is the weaker acid. It's always skewed toward the weaker acid and the weaker base. Okay, so that's what I just said. All right, so on the next slide, we'll see they have the relative strengths of acids ordered. And so we can, later on, we're going to use this idea because some things that can be even though it's a weak acid, then its conjugate can act like a weak base, and it'll be important in chapter 16. So here we can see the very strongest acids, and these were the 6 that I had mentioned before: HClO4, H2SO4, HI, HBr, HCl. Those are the very strongest acids, and then they go down from there. So those 6 are the most willing to give up an H+. Oh, the HNO3 is also one. And then going down, these are also acids because they're willing to give up their H+, but less so. There is an inverse relationship, so you can see that actually the strongest acids have the very weakest bases, because if HClO4 is really willing to give up the H, that means that the ClO4 negative is not very willing to take it back, and so there's this inverse relationship. And then you can see on the bottom the very strongest base is the OH negative, and those 6 bases, NaOH, KOH, LiOH, CaOH2, SrOH2, and BaOH2. Those are the only 6 that are completely dissociate to give OH negative, which is considered the strongest base. So you can see there's this inverse relationship. So we can predict the direction of an acid-base reaction by looking at that table. Since reactions always favor the weaker acid and weaker base, the stronger acid will always give the H+ to the stronger base, and you'll end up with the weaker acid and the weaker base. So if we want to look at this reaction, SO4 negative 2 plus HF gives us HSO4 negative and F negative. All right, so which side is favored? The left or the right? Well, we know it's going to go toward the weaker acid. So the first thing we want to do is pick out the 2 acids. Well, clearly HF is the acid on the left, and then HSO4 negative is the acid on the right. So then, which is stronger? You have to go back to the table and look at it, and I can't flip back while I'm recording this, but if you look at that table, you'll see that the HSO4 negative is stronger than the HF. So that means the reaction will shift or will tend toward the left. The reactions will go toward the weaker acid, which is from right to left. This is a similar kind of problem. It's just worded a little bit different. Will H2CO3 and HS negative react to give any products? Or in other words, is this a good reaction? Will this reaction go to the right? That might be another way of asking. So again, we want to figure out which are the acids. So on the left, it could be a little confusing because both of those have H's, but again, actually, they all have H's. So you want to see which one is the acid. The H2CO3 is an acid on the left, and the H2S is the acid on the right. Which is stronger? The H2CO3 is stronger if you go back and look at that chart. And so the reaction will go from the stronger acid to the weaker acid. So it will go to the right, which means that yes, a fair amount of products will be formed in this reaction. There's other ways of determining which acid is stronger than another besides just looking at that chart. And so when we do this, we're going to be looking at a couple of factors when comparing. Let's say we look at 2 acids and we say which one's stronger. We're looking at the structure of the molecule and looking at factors that will help us determine which one's stronger or less strong. And so this is a little bit different from that, but we can just look at molecules and determine which is stronger. So there are 2 factors that are important in determining how strong an acid is. The first is polarity. So if you have a polar bond, so making remember the H+, the H will be more positive, the X will be more negative. And the more polar this bond is, the better an acid you have. Because the more polar it is, that means the more skewed it is, the more the X will hold on to the electrons, the less the H will have the electrons, so the more willing the H is to break off. So the more polar a bond, the more acidic it is. The second factor is actually the size of X. So we do have, if we have a polar bond, that is important, but it's also how tightly is H held onto X from another point of view, and that would be how close is H to X. And so the bigger X is, the farther away H is, and the easier that bond is to break. So the larger X is, the weaker the bond, and the greater the acid strength. sometimes these two factors oppose each other, so we have to consider which one of these two factors is more important. So we're going to look at just a couple of different trends. The first one we're going to look at is binary acid. So first of all, what's a binary acid? A binary acid is one that has an H and one other element. It doesn't mean it has to only have one other atom, but it has to have one other element. So like H2O would be considered a binary acid. HF, HCl, they're all considered binary because they only have one other element besides the H. So as you go down a column of elements, the fact that the X atom, the second atom, gets bigger and bigger makes it a much stronger acid. So the bond strength decreases as the molecule, the second atom gets bigger, and so acid strength increases. So you can see if you're going down column 17, HF will be weaker than HCl, which is weaker than HBr, which is weaker than HI. If you looked at column 16, you would say, okay, H2O is a weaker acid than H2S, which is weaker than H2SE, which is weaker than H2TE. So same idea. As you go down, because the atoms are getting bigger, the bond is getting weaker, and the acid is getting stronger. As you go across a row of elements, bond polarity becomes the most important thing because they're all similar in size going across a row. So as electronegativity increases, the polarity increases and the acid strength increases. So this means, for example, that H3N will be weaker acid than H2O, which will be a weaker acid than HF. So going across the row, acid strength increases. Now we have the second kind of acid, which is called an oxoacid. And interestingly, that means that H is attached to an O, which is attached to some other element. And sometimes it's really hard to tell because the way we're doing it, we're writing the formula with the H in the front, so you can't, the formula doesn't always give the structure. So for example, acetic acid, which is HC2H3O2, is actually a little bit of a, you can't tell the exact structure. Sometimes you'll see acetic acid written as CH3COOH, and it's that one H attached to the OO, which is the acidic one. And the way we write it with the H in the front doesn't make it as obvious. But anyway, generally speaking, the H in an oxoacid, the H is attached to an O, which is attached to another element. So it turns out, so going from left to right, everything's the same. So if you go from left to right with a oxoacid, the acid strength increases. So again, well, there's not always that many oxoacids, but the main thing is that bond polarity is the important factor. So if you're going down a column, it's going to actually be a weaker acid because bond polarity, electronegativity, for example, F is more electronegative than Cl, which is more electronegative than Br, which is more electronegative than I. The bigger the electronegativity, then the more polar the OH bond is and the stronger the acid. So this is the opposite trend than what we saw for the binary acid. So HOCl will be more acidic than HOBr, which is more acidic than HOI. So going down a column. Often oxoacids have more than one O, so there could be other O's attached or other OH groups attached. And so whenever the more O's that you have with an acid, it's more electronegative, and so it will be more acidic. So the more O's you have, as long as you have the same central atom, the more O's you have, the more acidic you have. So you can see here that HClO is the weakest, HClO2 is stronger, HClO3 is stronger still, and HClO4 is a very strong acid. You could do the same thing with HBRO or HIO, any kind of oxoacids. The more O's you have, the more acidic it is. And then finally, if we're comparing polyprotic acids, so acids that have more than one hydrogen, we can rank their acid strength by how many hydrogens they have. So the more negative the acid is, the harder it is to remove an H, and so the less acidic it is. So for example, if you have H3PO4, that's much more acidic than H2PO4 negative. It's going to be much harder to remove that second hydrogen with the negative charge around. And then HPO4 negative 2 is an even weaker acid. So decreasing, if you've got more than one H, the fewer H's you have, the less acidic it is.